Hi, and welcome to Backer Breaks It Down. In this episode, we're going to explore logarithms and their properties. We're going to focus on converting from logarithmic form to exponential form and evaluating and simplifying expressions with logarithms. So let's check it out. So, previously we studied exponential functions. Most basic kinds look like this. F of x is equal to b to the x power. And remember, we referred to that b as the base of the function, okay? So an exponential function has an inverse that is also a function. And this inverse is the logarithmic function with base b, denoted log base b of x. Now, because they are inverses of one another, I can convert from like exponential form to logarithmic form and from logarithmic form to exponential form. Okay, so let's see how this is done. So remember, b is always representing the base of our exponential function, the base of our logarithm. So look, base of the log, base of the exponential. So the base is always going to be the base. Now, looking right here, okay, you'll notice the y is in the exponent spot. So we can think of it this way, that a logarithm is always equal to an exponent. So whatever the log is equal to, that's going to become the exponent in our exponential function, and then it's equal to x. Okay, so like in number one, I have log base b of 64 equals 3. So the base of my log is also the base of my exponential function. The log always equals the exponent. Okay, so b to the third power equals, and then I just fill in the rest. So the base of the log is the base of the exponential. The log equals the exponent, and we fill in the rest. Base of the log, 5. It's the base of the exponential. The logarithm is equal to an exponent, so my exponent is 2, and then I fill in the rest. Okay, so it's really simple. Base of the log, base of the exponential function, and the log equals the exponent. Fill in the rest. So because a logarithm is an exponent, we can evaluate simple logarithmic expressions using our understanding of exponents. And a few properties. First off, the one-to-one property of exponents. It says is if b to the m power equals b to the n power, then m equals n. So what this is like suggesting here is that if I get on both sides of my equation the same base, okay, so as a power of the same base, then I can say that the exponents are equal to each other. M, N, M equals N. Okay, so we want to get the bases to be the same, and then we can see the exponents are equal. Now there are some like tricks that we might have to use in order to get the bases to be the same. Okay, so you definitely want to know like your powers, like 2 to the second power is 4, 2 to the third power is 8, 3 to the second is 9, and so on. You want to know those, like, because that's going to make it quicker for us. But then we also want to know some other properties of exponents. And I've identified like 2 in red here that are kind of important. Like, how am I going to turn a fraction into an exponential? Okay, so if I have a fraction like 1 over something, I can take that something and turn it into like something with a negative exponent. So for example, in case you're like, what is going on here? If I had like 1 over, let's say 7, I can rewrite this as 7 to the negative first power. Okay. If I had like 1 over 2 to the third power, I can rewrite this as 2 to the negative 3 power. Okay. And so that's how I'm going to take simple fractions that are 1 over a number and how I'm going to write them as an exponent, like with a base with an exponent. And then I have these other rules over on the right-hand side that deal with radicals. So like we all know the square root of x is x to the 1/2 power. So I can basically take the nth root of anything and raise it to a rational root power. So for example, if I had like the cubed root of x to the fourth power, this rational exponent rule is saying I can write this as x to the 4/3 power. So notice that like this right here, the m divided by the n, that's the original exponent, and n is the index of the radical. Okay, but that's how I'm going to handle like square roots and other roots. Okay, so we're going to evaluate a logarithm. We're going to use exponents to do it because a logarithm is an exponent. I simply need to convert, and then I can use my properties of exponents to help me get the bases to be the same. So let's take a look at some like examples here that you have in your notes. So here's my logarithmic expression, log base 2 of 16. And so like if I think about the definition of logarithm, I'd be like, well, 2, like if I say this equals y, I'd be like 2 to the y power equals 16. So I'm thinking like, well, 2 to what power is 16? And so like I can rewrite 16 as 2 to the 4th power. Okay, so then I have like 2 to the y power equals 2 to the 4th power, which means that y is equal to 4. The exponents are equal. Okay, and so here, part B says log base 7 of 1/49. So like 7 to what power is 1/49? And so we recognize that like, well, I know that like 49 is 7 squared. So 1/7 squared would be 7 to the -2nd power. Okay, so then I have, 7 to the -2nd power is 1/49. Okay, so log base 25 of 5. 25 to what power is 5? Well, like, I know that the square root of 25 is 5. So I can rewrite the square root of 25 as like 25 to the 1/2 power. So I would have like 25 to my unknown equals, I'm rewriting 5 as 25 to the 1/2 power. So this one's like kind of funky, but I end up with 1/2. Great. But this is kind of like what we want to be thinking about when we are evaluating a simple logarithmic expression. So let's like see it from start to finish. So we're going to evaluate the logarithm by first converting it to its exponential form. And then we're going to use the properties of exponents to simplify the logarithm. So number 4, I have log base 3 of the square root of 3 is y. So I'm going to rewrite it in exponential form. Base of the log is the base of my exponential. The log equals the exponent. So I have 3 to the y, and then I fill in the rest is equal to the square root of 3. So now remember, like, this is what I want. I want to get the bases to be the same, because if the bases are the same, then I can say my exponents are equal. And so I have like this nifty little property here that says the square root of x is equal to x to the 1/2 power, which means that I can say the square root of 3 is the same as 3 to the 1/2 power. So then I have 3 to the y power is equal to 3 to the 1/2 power, and then m equals n, y equals 1/2. So get the bases to be the same, because then you can say the exponents are equal to one another. So let's try another one. So number 5, we have log base 5 of 1/25 is y. So the first step is to convert it to its exponential form. So the base of my log is 5. My log equals the exponent, so my exponent is going to be y. And then I fill in the rest is 1/25. Okay. So now my goal is to get the bases to be the same. So I have to think about 1/25, right? And so something that like jumps out at me is like, I know that like 25 is 5 squared. So I can think of 1/25 as being 1/5 squared. Okay, but remember, I have to have the bases be the same before I can say the exponents are equal. And so that's where this fraction rule we were talking about earlier comes into play, because I can rewrite 1/5 squared as 5 to the -2nd power. Remember, my goal is to get the bases to be the same. So I want on both sides of my equation base 5, okay? And therefore y is equal, yikes, sorry about that, y is equal to -2, okay? So we want to get the bases to be the same so we can say the exponents are equal. We had to like see 1 over 25 and be like, oh, this is the same as 1 over 5 squared. And 1 over 5 squared is 5 to the -2nd power, okay? And so that's how we can evaluate simple logarithmic expressions. So we're talking about where the unknown or the variable like y is on the outside of the log. And so when we have log equals our unknown, we're going to convert to its exponential form, and then we're going to get the bases to be the same so we can say the exponents are equal. And that is how Becker breaks it down.